Welcome to Khetz Tutorials, and in this video I'll be talking about tangents to graphs or functions. So let me write that down quickly. Tangents to graphs. That's all I'm going to write, I think. So now, what is a tangent? A tangent basically is a line, so we can write that down as well. It's a line, but not just any line. It is relative, or it is with respect to another function or a graph. So we can't basically call just about any line a tangent. So if we have a line like that, we can't really call it a tangent because it's by itself. Now, when we call a line a tangent, it basically touches another function, right? Then one would ask, let's say, what exactly do you mean by it touches another function? If I have a straight line which passes through there, is it a tangent? If I have another line which passes through there, is it a tangent? And both of these are not tangents, and here's why. We have to further specify how this line basically touches another function. It touches another function, or touches a function once. So it is at a specific point, at a point, so at one point, at one specific point. So one tangent can only touch a function once. So let's say we have that function over there, that graph, and we have a line which passes through there. It has to touch this function once for it to qualify, or for us to call it a tangent. So summing everything up, we can say that a tangent is a straight line which touches another function only once, or at a specific point. So that is the basic definition of what a tangent is. But now let's see what we can do with all of this information, or how we can actually calculate stuff which is associated with the tangent. So now, a tangent is a line. It is a straight line. So let's talk about straight lines. I think that is the best thing to do, because we are now talking about the nature or the behavior of tangents. Now, you know that a straight line is defined by y equals to mx plus c. And now you have your m as the gradient, the c as the y-intercept, and y just being a function of x, or something which results after you substitute a certain x value. Okay, so we know that much. But let's say we have a graph, and going back to what we've been talking about in the previous video, the derivative of this graph at any point, or at a specific point. So if you find the derivative of a graph at a specific point, it is basically the gradient at that point. Now, what do we know about straight lines? If you have a straight line like this, that, or whatever the case may be, the gradient is basically the same throughout this line, or throughout the whole line. So the whole line basically has the same gradient, whether you're here, you're there, or anywhere else. It basically has the same gradient, right? It's either decreasing or increasing, or it basically takes on a particular value, a particular function. That is what we know. So now, if we can, or if we know that the derivative at a specific point of a graph, let's say this parabola over here, has a certain gradient, then we can use that information to our advantage. And here's how we'd use it. So if we have a parabola, or whatever the case may be, and we can find the gradient at that point, and we know that our tangent passes through that exact point, and the derivative at that point is the tangent, is the gradient, right, at that point. So let me change this. Here, we know the gradient. So once we know the gradient there, then that means that we know the gradient of the whole line, because we just mentioned, or we know that the gradient throughout the line is the same. Now, if you can use the white graph, this graph, if you can use it to find the gradient at a specific point, then that point has the same gradient as a tangent which passes through the point. So now we have talked about a few things. So let's try to summarize all of that stuff. So a tangent is a straight line, and it touches a graph once. And what else do we know? We know that we can find the gradient at a point using the derivative. And once we find that gradient at a point, and we have a tangent, which is a line which passes through the same point, then we know that we have the gradient of the tangent. Once we find the gradient at a point, and we say that the tangent passes through that exact point, then we know that this gradient there is the gradient of the whole tangent. So what we have to take away from this, or what we have to note, is that a tangent passes through or it touches at a specific point. So these are the only things that you have to worry about with regards to this information, because you'll always be asked to find the gradient at a point, or they'll ask you to find the point where a tangent with a certain gradient passes through, or you'd be asked to find, what else can they ask? Let's see, what else can they ask? Something related to these things. So it's always about the gradient at a point, it's always about the gradient of the tangent and a specific point. Because if you had another point here and you found the gradient there, but you wanted to find the gradient of this tangent, then that would be wrong, because this yellow tangent doesn't pass through that point. So all of this happens at a specific point. So now let's talk about a few examples, or before we even get to examples, since we're talking about straight lines, let's talk about a few more things that we can consider as revision, because I assume that you have done functions or stuff like that. So I basically said that you have this as your general formula for a straight line, and this is your gradient, and I explained all the other things. Another thing that you can note is that if you have an x coordinate, then f of x will be your y. And another thing that we can talk about, when we say that straight lines are parallel, we basically mean that they never touch. So basically there's something like this. And what you note, or what you can notice from parallel lines, is that they have the same gradients. So if a certain function y1 and y2 are parallel, so if y1 is parallel to y2, where y1 and y2 are defined by such a formula, then we can say that the gradient of y1 is equal to the gradient of y2. So in summary, or as to summarize this, when we have straight lines which are parallel, like in this case, we can assume that these two lines are parallel, we can say that they basically have the same gradient. So parallel lines have the same gradient, right? So that is the case. And what else? When we have perpendicular lines, so let's say now y1 and y2 are perpendicular. This is how you show it, perpendicular, and this is for parallel. When you have this case, then this changes into this. So the gradient of y1 and the gradient of y2 will be shown by these. Now, if you multiply the two gradients, they should give you -1. This, I believe, is just revision, because there might be some questions which are related to this, where you're asked to find a line which is parallel to the tangent, asked to find a line which is perpendicular to the tangent, or stuff like that. So I just wanted to mention it in passing. And now let's get back to what we were talking about. So I'm just going to leave this up here because we might use it. So let me say, if you find the derivative of a function, might be a parabola, whatever the case may be, then you can find the gradient at a point. And after finding the gradient at a point, if you know that a specific tangent passes through this same point, then that gradient at that point is equals to the gradient of the tangent, because the tangent is a straight line, and once again, the gradient of a straight line is basically the same throughout. So let's start with an example. We're now moving on to examples, and the first example that I will do is as follows. So let's say we have f of x equals to 2x squared minus 6x, right? So this is a function that we have, and from theory, we know that this is a parabola. It should look something like this. The coefficient of x squared is basically positive, so we expect it to look like this. Even though we are not specifically sketching it, we're just trying to visualize what's going on. That is what I'm doing with the yellow thingy over there. Now, okay, let's say we are asked to find the gradient of the tangent to the curve at x equals to 3. So what is the gradient of the tangent to the curve at x equals to 3? And this is my own notation. I don't think I've seen it anywhere else. I'm basically just saying the gradient of the tangent And remember, the gradient of the tangent has to be with respect to this graph. Now, once again, I did say that if you find a point somewhere there, or if you find the gradient there, but your tangent is actually on this side, then that would be wrong. So this is at a specific point, and the specific point is x equals to 3. So let's say x is equals to 3 somewhere there. Now expect our tangent to be something like that. So basically it touches something somewhere there, basically at x equals to 3. And we're now asked to find the gradient. Now up here, I wrote that if you find the derivative of a function at a point where your tangent actually touches, then that means that the gradient at that point is the gradient of the tangent. So all that we have to do when we're asked to find the gradient of a tangent is to find where the tangent basically touches the function. And in this case, we're given that point. We know that the tangent touches at x equals to 3, right? And we have the formula of our function, the yellow function. We have it over there. Once we find the derivative of this, we know that that would be the formula of the gradient. And once we substitute this point into the derivative, then we know the gradient at this specific point. Once we know the gradient at that specific point, then we know the gradient of the tangent. So let's do that. So now finding the derivative of this, and if you aren't familiar with differentiation and stuff like that, I do have a video, and I'll just link it to this video. So now finding the derivative of the original function, so we denote this with f prime of x. So f prime of x, it would be 4x minus 6. And now we want to find, this is the derivative, which is the gradient. And we want to find the gradient at a specific point, and that specific point is 3. So we're going to say f prime of 3 equals to 4, then substitute 3 in there. This should be 12 minus 6, which is 6. So we know that the derivative basically at 3, x equals to 3, is basically equals to that. And this value is exactly equals to the gradient of the tangent at 3. So that is all that we had to do in that case, and we can now move on to another example. I want to do a few more examples just so we see how all of this works. So the second example, I guess we can say that it's in increasing levels of complexity, if you want to basically put it that way. So yeah, the next one, let's say we are given g of x equals to x squared plus 3x minus 4. So let's say this is the function that you're given, g of x, and you're asked to determine the coordinates. Now, remember in the previous question, we were given the point, we are given the equation of the function, and we're given the point, right? But now, if you look at this, we're given a function and we're asked to find the point where some tangent basically passes through. So as you can see, it always revolves around certain things, right? So we can say the gradient of the tangent, the point of intersection, or the point where the tangent touches, and maybe the equation of the tangent, something like that. You can always view it as a circular relationship or whatever you want to call it, but those are the basic things. The definition of a tangent will always be what they basically ask. It touches at a specific point. It is related to a function, and at that point, if you find the derivative, you now have your gradient, or the gradient of the tangent, basically. Now let's write this question out, and I am just repeating this stuff just so it actually sinks in and you don't overcomplicate this kind of stuff. So now, given g of x is equal to all of this, we are asked to determine, or should I type this? No, let me just write it. Determine the coordinates of the point on the curve G where the gradient of the tangent is minus 3. So now you can pause this video and try to understand what they're actually asking for, or how you'd actually I did explain what they're asking for. They're asking for coordinates, which is basically the point where the tangent passes, or where the tangent touches. I did explain that. So now you can pause the video to maybe try and see how you'd approach this question. Okay. Hoping that you actually did that. Even if you didn't, don't feel guilty. That's fine. I'm here so that we can actually go through this. So let's go through this. So we now want to find, once again, this can be seen as some sort of parabola like that. It has a positive coefficient of x squared, so expect it to look something like that. And now we're saying that we want a point where the gradient of the tangent is -3, and this is a negative gradient, so expect our tangent to be maybe something like that. But we don't know where it touches, so we can't really assume where it touches, but we can assume that it actually looks something like this, because the gradient is given to us as negative. So this is not an exact point, or let me say, at this point, we can't tell what that point is. And that is our assignment. That is what we have to do. We have to find that coordinate, or those coordinates of that point. So how would you do that? Now, looking back at everything, you just have to stitch up all of this. So most of the times you'll have to reverse engineer the stuff and just work with it in a reverse manner, I guess. So now, if you find the derivative of this, which should be that, this function should give you the gradient at any point, right? So this is the gradient along the graph, along the white graph. That is the gradient. Now we are given the gradient, so we can equate this to the gradient that we're given. And if we equate this gradient formula to the gradient that we're given, we can find where that gradient holds, where this gradient holds. So we know the gradient, but we don't know where the gradient holds. So that is what we want to find. We want to find the x coordinate and later on the y coordinate that should actually give us this value. So this answer basically means that at x equals to 3, we have that gradient. But not just anywhere. We have to find the y coordinates by substituting this back into the original. So don't make the mistake of substituting this into this function, because this is the derivative, which is the gradient formula. We want an exact coordinate, so we substitute back into the original formula up there. Now, if you do that, then we basically come here and say, let's see what we get. So equals to -3 squared plus 3 minus 3 minus 4. So that is what we have over there. And g of -3 should be equals to 9 minus 4. So only the effect of this is left because these two cancel out. So you have -4. So that would be your y coordinate. And now our coordinates are basically -3, -4. This is your answer. This is our answer. And from all of this, you can see that we were given the gradient and we're given the formula of the function. And we know that from the formula, we can find the gradient. So from the formula, we can find the gradient. But we don't know where this particular gradient was, or where the tangent actually has to touch. And that is what we found down here. So after finding where the tangent touches, we basically substituted that x value into the original g of x to find the corresponding y value. And we now have the coordinates of where we expect our tangent to touch. So we can now say that this should be somewhere or exactly at -3, -4. That point over there. So we now know where the tangent should touch. And that is what the question was asking for, basically. So now let's move on to, let's say, the last example. I just want to cover one more example. And I guess we can say we are increasing some complexity, if you want to put it like that, but the basics or the concept is the same. So let's say, for example, not for example, this is indeed an example. So let's say we have a question which says, determine the value of P if the line given by y equals to negative 2x plus p is a tangent to y equals to negative x squared plus 4x plus 5. So once again, let's do our checklist, if you want to call it that, once again. So this is our tangent formula. Remember that circle thing that I drew, and this is our tangent formula. And we have the formula of the function that we're dealing with, right? And now we have a partial definition of the tangent. So the only thing that's left in this function is the p, right? So we have to find that p. So the question basically says, what is the p? But what is the relationship between the tangent and our function? We know that if we find the derivative, we can call this f of x because it's not truly defined as any other letter. So we can call it f of x. That is safe, I believe. So if we transform it to this, or if you want to do it this way, which doesn't exactly allow, this notation doesn't exactly allow us to actually show that we're substituting something. So let's rather go with this notation. Let's go with this notation. So let's say this is f of x. You can name it any other letter, doesn't really matter if it's not mentioned. So now let's say that this is what we have. We know that if we find the derivative of this, which should be that, then we can find the gradient of the tangent. But if you look at the tangent, we aren't really given the point where the tangent passes. We don't know where this tangent particularly passes, right? So we aren't sure at this point where the tangent passes, but there's something that we do know. If you remember from the definition of a straight line, this m is the gradient. So whatever point that is, even though we don't know the point, we know that at that point we should have a gradient of m, and our m in this case is negative 2. So we can equate this gradient formula to that particular gradient over there, which is the gradient of the tangent. So we know the gradient of the tangent, we can just extract that from the formula. Now that we know the gradient of the tangent, we can now find the exact point where the tangent basically passes. And if we do that, we basically get this. And after getting that, we can now substitute it back to the original formula, which is f of x, which is this one up here. So substituting it in the original formula, this is what we get. So negative 9 plus 12 plus 5, this is 3, added to 5, that's basically 8. And our coordinates are now 3, 8. So we know now that the tangent is expected to pass through this point. And we have a partial definition of that tangent, which is this. So we can now substitute this point, which is on the line, so that the point where the tangent actually touches our graph is on the line, obviously, because it touches at that point. So we can now substitute this point into this equation to find our p, which should be our answer. And doing so, you get your p as 14, right? And here's how we got to our answer, or here's how we did that. Just try to remember that you'd always, when dealing with tangents, you'll always deal with a specific point. You'll always deal with a straight line because a tangent is a straight line. You'll always deal with the derivative because that is how you find the gradient of the tangent, or the gradient at a specific point. And these are the basic things. The tangent passes at a specific point. You have to find the gradient at that specific point to find the gradient of the tangent, and then define it using this formula. But it can always be swapped around. Like in this case here, we're given a partial definition of the tangent, we're given our function. But we know that if we find the derivative of this, we can find that negative 2, which is the gradient of the tangent, which is this thing. And once we have that, we can find that specific point where the tangent passes, because we aren't given the point. If you were given the point, it would be much, much simpler. But now we had to find the point first. After finding the point, then we came back to the formula of our tangent to find that p. After finding that P, that is how you answer the question. So it will always be mix and match, but these are the basic things. You'll always have to deal with these things. So I hope this was informative. I hope this was of value to you. I hope this was helpful. If you have any comments, if you have any questions, just leave me an email, or you can leave a question in the comments, or anything you want to say. And if you like this video, just go ahead and give it a thumbs up. If you want to book a session with me, a private session over Microsoft Teams or any other platform, you can also email me to book a session. So that is it from me in this video. I will see you in the next video.